So my presentation is going to be called Are Two Better Than One? A comparison between single and dual monitor workstation in productivity and users' window management style. So these are the authors' names, and it was posted about a week ago in the International Journal of Human-Computer Interaction. The authors are expanding on existing research and attempting to determine if dual monitor workstations have any effect on productivity. It's very common to see multiple monitors being used in the workplace. The theory is that additional screen real estate through a second monitor could be helpful, since computers users typically multitask and have many windows open at the same time while working. Several past studies analyzing the use of multiple monitors in the work environment indicate that productivity increases when dual monitors are used in place of single. However, these studies are done with very simple tasks, or they tend to be quite limited when it comes to the measurements taken. Previous studies have lacked a thorough understanding when it comes to how users manage multiple windows differently, especially as task complexity level increases. Overall, many of the past studies noted in this paper demonstrated the benefit of having multiple monitors, but the majority of the cited research tended to concentrate on very lightweight computer tasks like entering text, searching for information from websites, travel planning, or calculating expenses. Very little work has been done with more complex, specialized engineering tasks that are often done in the workplace. In addition, the metrics that were used in past research are often performance-based and do not focus on metrics related to Windows switch and mouse use, such as cursor movement and mouse clicks, and the number of window switches. The author believes that these are required in order to better understand the physical efforts required to perform these tasks. The purpose of this study is to provide further insight into the use of multiple monitors in performing simulated engineering tasks with different levels of complexities. The authors wish to study how users manage multiple windows to perform their tasks in order to better understand strategies of window management by users, and how these various strategies have the potential to change as task complexities level change. That leads me to where the author's motivation lies, in expanding our existing knowledge of how users manage tasks of various complexities on single versus multiple monitors. Are multiple monitors really a time saver in all cases? Are there certain cases where the main advantage is simply user satisfaction and self-reported perceived productivity? I'd like to point out that this relates closely to Unit 6 of our course, which discusses user interface and interaction methods. Section 1 covers input technologies, and Section 2 covers user interface toolkits. These sections cover different input techniques and their underlying principles, and the special conditions under which each of these input techniques are most effective. There are 4 authors for this paper, and their motivation is not explicitly stated. However, Dr. Ling is an associate professor. She expresses interest in human systems integration and human-computer interaction in complex systems. Mr. Stegman is an industrial engineer with a Master of Science degree and has experience in human factors analysis, logistics systems analysis, and process improvements. Mr. Barbtaya is a plant manager with a Master of Science degree and has broad experience in human factors, process improvements, and lean manufacturing. Dr. Shahab is a professor and director of the School of Industrial and Systems Engineering, and she works in a multidisciplinary research group investigating factors related to equity and diversity in engineering students. Each of these authors has a hand in the pot, and they all bring both academic and industry experience to the paper. A pre-study survey was performed, which had input from 29 engineers employed in a technical office setting. It had questions related to software applications used, monitor configurations, and frequency of use of dual monitor settings. The tasks were designed to simulate the activities performed by an engineer in a technical role. Information on multiple windows was simultaneously presented, and other tasks would arrive via email. Typical software such as AutoCAD, Microsoft Excel, Microsoft Outlook, and Internet Explorer were used. 3 levels of task complexities were designed by varying the number of windows needed to perform tasks, 2, 3, or 4 windows. A total of 6 tasks were designed, with 2 versions for each level of complexity, a version A and a version B. This table shows the tasks, software, and task descriptions. Tasks requiring use of more windows have higher complexity levels. It requires more cross-referencing among multiple windows, and it poses different levels of problem-solving demand to the users. For all tasks, the task instructions were sent to participants via Outlook email with reference documents as an attachment. After the participants finished the task, they email the finished documents as an attachment back to the experimenter. There were 34 participants aged 18 to 39 years old, average age of 23, with a standard deviation of 3.5 years. All participants were right-handed, normal vision. All had knowledge of the basic functions of software applications being used, and they were all from a technical discipline such as engineering, architecture, or business. Participants performed 6 tasks, 3 on single monitor setting and 3 on dual monitor setting. Various controls were used, such as varying the sequence between participants, gathering self-reported proficiency levels, and basic training for tasks beforehand. In addition, the order effect was controlled for by using a counterbalance table for each participant. Lastly, a post-completion survey was given, asking their opinions and preferences on the monitor configurations. In Task 2A, participants read email instructions from Outlook and performed tasks in Excel. Information was recorded in Excel, and each component was given a different colored product sticker. They were then asked to calculate the total number of stickers for each color needed in the assembly, input those numbers into an Excel spreadsheet, and then construct a pie chart for each assembly, highlight certain cells, count certain cells, and input those numbers into another Excel spreadsheet. Task 2B asked participants to complete a financial assessment for 4 stores, including a long list of calculations. The participants then used this information to answer questions about the store's profitability. 3 window tasks, called 3A and 3B, both used internet searches for products listed in Excel tables attached to the emails. The participants would first use Outlook to fill in the Excel spreadsheets and search specific sites for prices using Internet Explorer. Task 3A used Amazon.com as its source for parking lot materials, while Task B used Dell.com and ToshibaDirect.com as their source for computer parts. 4 window tasks, 4A and 4B, were the most complex. Internet Explorer was used to gather information, and then using the information from Outlook and Internet Explorer, graphs were drafted in AutoCAD, and calculations were performed in Excel. For Task 4A, participants were then asked to draft a parking lot design based on the expectations, along with an attached image in the email. The participant was asked to count the total number of spots present within their drawing. Using this information, with operating and material costs provided in the email, the material costs obtained from the internet, the participant was asked to calculate the total construction costs, operating costs, and revenue of the parking lot. They were then to use this information to determine the parking lot's first-year profit. 2 independent variables were used in this experiment: monitor configuration, single or dual monitor, and task complexity, 2, 3, or 4 window tasks. Both are within subject factors. This is when an independent variable is manipulated by testing each subject at each level of the variable. The dependent variable includes 4 measures: task completion time, number of mouse clicks, amount of cursor movement, and number of window switches. Software called Moray was used in order to capture all user sessions. Keyboard shortcuts like Alt-Tab were prohibited in experimental instruction. All actions were performed using the mouse only. Number of mouse clicks were quantified by the total number of left clicks on the mouse during tasks. The cursor movement was quantified as the number of pixels that the cursor traveled during tasks. Lastly, the number of window switches were recorded by researchers viewing video recordings. Here's a summary table of the results for the 4 productivity measures with the 2, 3, and 4 window tasks, both on single and dual monitors. Mouse clicks, cursor movements, and window switches were all recorded. When it came to task time, the task complexity factor was significant, but no significant differences were found between single versus dual monitor configurations. For the number of mouse clicks, significant differences were found both in the monitor configuration and task complexity. Dual monitors consistently resulted in fewer mouse clicks than single monitors. As for the cursor movement, no significant difference was found between the single and dual monitor, but there was a significant difference in cursor movement for task complexity levels. For the number of window switches, significant differences were found in both monitor configuration and task complexity. Dual monitors resulted in fewer window switches than single monitors.
The background literature focused on in this paper were centered around two different topics: productivity comparison between single and multiple monitor settings, and window management style on multiple monitors. For the related research on productivity, various papers suggested advantages of dual monitors due to the additional screen real estate. Research found that participants were performing tasks 9% faster with larger displays versus smaller displays. According to the paper, errors were occurring with smaller displays, such as accidental closing of files and frequent resizing of windows. These errors were less common when using a larger display. 14 out of the 15 participants preferred the larger display. Another study showed that the productivity of single, dual, and triple monitors, they had participants perform various text, slide, and spreadsheet tasks. The results indicated that multi-screen configurations were scoring significantly higher on every measure that they used. Another study compared single and dual monitor setups, and they found that multiple monitors were able to help reduce the overall task times while they were performing online air ticket booking tasks. Lastly, one study found that dual monitors were associated with higher productivity than single monitor, regardless of the monitor size when users completed office tasks. More space on dual monitors means a reduced need to switch between windows. Using software to automatically gather data over an extended period of time, researchers found that single monitor users switch windows more frequently than multiple monitor users. Additional research reported that the moving and resizing of windows were reduced in multiple monitor configurations. The thought was that larger screens could potentially reduce the user's efforts with window management, therefore reducing their cognitive load. Users who switched from single to dual monitors were very unlikely to switch back. To summarize, the past studies have demonstrated the benefit of having multiple monitors. However, the majority of research concentrated on lightweight computer tasks. Little work has been done with more complex, specialized engineering tasks in the real-world workplace. Additional metrics are needed when it comes to window switching and overall mouse use, as these would help to understand the physical efforts expended to perform such tasks. Focusing on usage patterns with multiple windows, one paper summarized different behaviors exhibited by users while managing window spaces based on user interviews. They identified three main window management strategies: maximizers, near maximizers, and careful coordinators. Maximizers keep windows at the maximum size while using Alt-Tab or the taskbar in order to switch between windows. Near maximizers have their windows taking up most of their screen real estate, but leave some of their desktop icons visible. Careful coordinators, on the other hand, tend to resize their windows often, ensuring that several windows are visible on the same screen at the same time. Another study called its user styles either Alt-Tab users or mover resizer users. Another strong point of the study I'm focusing on in this presentation was that it aimed to simplify the process of determining user styles by categorizing user window management styles as toggler and resizer. Basically, whether users can view information from multiple windows simultaneously or not. A toggler toggles between windows to view and interact with an open window, while usually occupying most of the screen with one window. Therefore, a toggler user cannot view multiple windows at the same time on the same monitor. A resizer, however, resizes multiple windows to view the contents of multiple windows at the same time. They spend time and effort moving and resizing windows in order to see multiple windows on the same monitor. This categorization allows us to simplify so that both maximizer and near maximizer fall under the toggler category, and careful coordinator falls under the resizer category. Toggler is similar to the Alt-Tab style used in other papers, and resizer is similar to the mover resizer. So, one thing I wanted to critique while we were here is the author's decision to come up with a new standard, in an effort to overcome the competing standards. The various words used to describe the window management styles, such as toggler, resizer, etc., add a layer of abstraction that, while aiming to simplify, can make the research more confusing. Another thing I wanted to point out was that the keyboard shortcuts were prohibited in the experimental instruction. This is not realistic for all users. Keyboard shortcuts are a major component of interacting with an operating system efficiently. By banning keyboard shortcuts and enforcing only mouse use, the experimenter was not reflective of all users. Right clicks were also not recorded, only left clicks, but no explanation was provided. The results outlined in this paper do partially support the hypothesis that there is a benefit of having multiple monitors. While dual monitors did not significantly reduce the time or amount of cursor movement, it did significantly reduce the user's effort of mouse clicking and switching between windows. In addition, the users overwhelmingly preferred the dual monitor configurations. They truly believed that they were spending less time on tasks with dual monitors. Window management efforts were also reduced, and users' task execution efforts were reduced because they made fewer mouse clicks. Results indicate that as the task complexity increases, users spend more time and more effort on cursor movement, mouse clicks, and window switches to meet the task demands. When the task becomes more complex, users adopt the resizer style in order to view more information simultaneously. The contribution of the current research is threefold. Additional measures were studied, including the amount of cursor movement and number of mouse clicks, to get a complete picture about the user's physical efforts in task completion. Also, realistic office tasks of different levels of complexity were used. All tasks were solution-oriented and designed based on a survey of working engineers. These tasks are not repetitive in nature, and participants are not familiar with the tasks. Therefore, the paper's results are more generalizable to the real-world engineering tasks. In addition, the author proposed a new way of categorizing a user's window management style.
Many limitations exist in the study, even as reported by the authors. One issue is that goal or operator method selection, or GOMS analysis, is based on expert user performance. In this case, much time was spent on understanding the task rather than executing. Significant differences in task time were not seen, and this could be a reason. One way to fix this could involve designing routine tasks, or by providing extensive training. In addition, the study was lacking an assessment of task quality. Lastly, about half of the users reported being unfamiliar with all functions of AutoCAD, even with training, so task time was longer for the 4 window tasks. I'd also recommend for any future research done on this topic of study that no further competing standards are introduced. I'd recommend simplifying by utilizing the available terminology rather than reinventing the wheel.
Thanks everyone for taking the time to listen. I'm looking forward to hearing your questions.